The main focus of this video is to derive the Cauchy-Schwarz inequality for vectors. Cauchy-Schwarz inequality for vectors, which is of the following form. Here at the left hand side I have the product of the u and w in little l1 norm, which is the counting measure, and at the right hand side I have the product of the u in little l2 and w in little l2. So what is the proof here? So we take the quantity sum from I equals 1 to n. We take the sum from I equals 1 to n of lambda ui plus wi to the power of 2. So this is lambda times u1 plus w1 squared plus lambda u2 plus w2 squared plus lambda un plus wn squared. I expand the brackets. This is a known identity, so it's lambda squared u1 squared plus 2 times lambda u1 w1 plus w1 squared plus lambda squared u2 squared plus 2 lambda u2 w2 plus w2 squared plus lambda squared un squared plus 2 lambda un wn plus wn squared. What can I get from here? This one, and this one. So the terms that have lambda squared, I can write lambda squared as a common factor, and inside inside the brackets I have the sum u1 squared plus u2 squared plus un squared. Plus 2 lambda, again I take common factor, and inside I have products of ui's and wi's, u1 w1 plus u2 w2 plus un wn plus now the w's, w1 squared plus w2 squared plus wn squared. This can be written as lambda squared. This is the sum from I equals 1 to n, ui, the magnitude squared, plus 2 lambda, the sum from I to n of ui wi, plus the sum from I equals 1 to n wi in magnitude, the magnitude of wi squared. So this is a polynomial, let's call it g of lambda squared. This is the coefficient of this sum is the coefficient of lambda squared plus 2 lambda. This is the coefficient of 2 lambda here. This is coefficient of lambda squared, coefficient of 2 lambda plus the constant term here, which is this sum over here. Now let's find what is the, in order to have this quantity here to be bigger or equal to 0, this polynomial here should have either a double root or no real roots. So the discriminant should be less or equal to 0. The discriminant, because it's a polynomial of degree 2, is equal to this one squared minus 4 and the product of these two sums. So I have that when I take the squares here, 2 squared is 4 and the 4's go away, so I will have the sum from I to n, the ui wi should be bounded by the sum from I equals 1 to n of the ui squares, the sum of the ui's, and wi's to the power of 2. And then from here I have that I take the absolute value of this, and here I take the square root on both terms. Or this can be written as the following. I can obtain the following bound. This can be written as so this is ui, let's call it u times w. This is the little L1 norm, bounded by the u little L2 times w little L2. If we want to find the, let's say, the norm of a L2, little L2 is the sum from I equals 1 to n of alpha I squared, and then you take the square root, or you can write it in modulus this one, and then you take the square root. This is the little L2 norm. And here I have finished my proof.